today, but yeah, I just totally blanked on mentioning it last week, so we're pushing it back till next Tuesday, so a week from today. So exam 1 is Tuesday, February 7th. And the topics will be everything up through those vectors problems. So the stuff we're working on right now with 2D kinematics, that won't be on it. And I think what I'm going to do generally is I'm going to give you a sheet of equations. That's the one they give you for the AP test, so you can get just used to working with that, because I know most of you are going to end up taking the AP test at the end. But for this one, I'm just going to, I don't have those to give you yet, so I'm just going to write all the equations that you need on the test. So you don't have to remember any equations or anything. It'll be on there. Any questions about the test? Okay. Any homework questions? Seven through 9? Does anyone have it with you? I don't have them printed out in front of me. I guess I can pull them up here. These are the vector problems.
Yeah.
All right. Oh, okay. So all the ones with 2D kinematics. All right. So number 7 says, think about this vector equation. Position final is equal to position sub 0 plus V0 times T final plus 1/2 A vector times T final squared. And, you know, this is a vector-looking version of the one of the kinematics equations along a line, right? And so we're just going to break this up into components, do the vector math, and then think about what it tells us. We haven't talked about this equation yet, but it is an equation that we're going to use when we start talking about 2D kinematics. So in component form, this says PFX, PFY is equal to P0X, P0Y plus V0X, V0Y times TF, and TF isn't a vector, plus 1/2 times the vector AX, AY times TF squared. And using the rules of vector math, I can rewrite this as PFX, PFY is equal to P0X, P0Y plus V0X times TF, V0Y times TF. Because when you multiply a vector by a scalar, you just multiply the scalar to each component. And then this one says one half AX. Yep. Yes. Okay, bye. So 1/2 AX TF squared, and then 1/2 AY TF squared. And that gives us two different equations, two independent equations. The first one says PFX is equal to P0X plus V0X TF plus 1/2 AX TF squared. And the second one says PFY is equal to P0Y plus V0Y TF plus 1/2 AY TF squared. So, okay, that's number 7. Number 8 and number 9 are basically the same idea as that. Why don't you just take your assignments back, do number 8 and number 9 like this, okay, and just bring them back on Thursday along with the new stuff I assign, all right? Any questions about that?
No, but for number 5 for direction, did you just mean like the angle?
5. Oh, okay. So for number 5, this is going to be an important way for us to think about vectors. Say that, so part A says, if you know you have a vector right and a vector up and they're added together, what are the possible directions of those vectors? So a vector, so let me draw a couple of these. So a vector to the right plus a vector up. You could have a tiny vector to the right added to a big vector up, and you'd get, your resultant vector would be basically just straight up, right? It could be as close to perfectly up as you want, just based on the ratios of those. Or you could have the opposite extreme where you have a big vector to the right and a tiny vector up. And so you can get as close to vertical as you want. I mean, if you get to control how big these vectors are, or if you don't know how big they are and you're just trying to figure out a range of possible values, it can be infinitely close to vertical, infinitely close to, well, to you, to the right, But it can't be, by changing the lengths of these vectors, it can be anywhere in between those. Does that make intuitive sense? Like I could make this twice as long and then it's like that. I could make them the same length and then it's at 45 degrees. Okay. But I can't do anything to make it go past vertical or below horizontal. So if you know the directions of the two vectors you're adding, but you don't know the magnitudes, then you know the sum within one quadrant, always. Okay? There's a range of 90 degrees of possible answers. Okay?
Okay.
So, you know, this whole world of directions is possible in that one. Or if you put the two vectors tail to tail, you know, any vectors pointing in these directions is possible. For B, if you have a vector left and a vector down, and you don't know the magnitudes, then any of these vectors are possible, but nothing in the other 270 degrees. And we're going to think about a lot of stuff in that way, where we don't know the magnitudes, but we can pin the directions down to a 90-degree slice. Any other questions? Okay, so yeah, if there are any questions on today's homework that you haven't done, it sounds like that's the case for a lot of people, bring them home, finish them, and just bring them back on Thursday, okay? All right, so last time we talked about, we started talking about 2D kinematics. And we talked about the position vector, the meaning of the position vector. And if you want to plot the position vector, you know, since there's two components now, we can't really plot just plain position versus time anymore. But there are three useful graphs that we can think about. The first two are the components of the position vector versus time. So the x component of position versus time. The y component of position versus time. And then the third one is a plot of the motion. It doesn't show time on it. And I'll write that as py versus px. That shows the path that the particle is following. Okay, so let me do an example and show you what these three look like. So let's say that the position vector as a function of time is 5t negative t squared. then a plot of the x position versus time. This is the x position, this is time. We're just plotting the function x equals 5t. So it's going to look something like that. That's 1, 2, 3, 4, 5. And then we can also plot the y component versus time. And that's going to look like this, a downward parabola. And then the last thing we can do is show the path the object follows with px on the horizontal, py on the vertical. And for this one, you can just plot points like what's the position vector going to be when time is equal to 0? 0. It's going to be right at the origin. What's the position vector going to be when time is equal to 1? 5, -1, yep. So that would be, say here. When time is equal to 2, what's the position vector? 10, yeah, -4. And so something like that. And so this is a picture of the path that the object is following in space. It doesn't show time in it. Like you can't tell where along this path the object's going to be at what time, but it shows the path the object's following. And that's going to be important in understanding velocity and acceleration. Any questions about those? Okay, so the next thing we have to talk about is the instantaneous velocity vector. Or what we're just going to call the velocity vector. So the definition of the velocity vector as a function of time is the time derivative of the position vector. So for example, if the position vector is a function of time, I'm going to use the one I just used, is equal to 5t negative t squared. Then the velocity vector as a function of time is equal to 5 negative 2t. The velocity vector has a magnitude that's equal to the speed. And a direction tangent to the path of motion. on a px versus time graph, the slope of the tangent line, or let's say the Vx, the x component of the velocity vector, is the slope of the tangent line. On the py versus time graph, Vy is the slope of the tangent line. And on the py versus px graph, the object path, the velocity vector is in the direction tangent to the curve. Okay, so here's an example. Let's say the position vector is equal to 10 times the cosine of 2t and 10 times the sine of 2t. Let's find the velocity as a function of time. Let's show the x component of the velocity at time equals pi over 4 on a px versus t graph. Vy at time equals pi over 4 on a py versus t graph. And the direction of the velocity vector on a py versus px graph. That's the path, the one that shows the path. Okay, so first of all, to calculate the velocity vector as a function of time, we're just going to take the time derivative of the position function. So v as a function of time is just equal to the time derivative of position. And that is negative 20 times the sine of 2t, positive 20 times the cosine of 2t. Second, we want to show on a position versus time graph, on a x position versus time graph, what the x component of velocity is at time equals pi over 4. So if we plot the x position versus time, it's a cosine function with an amplitude of 10. At time equals pi over 4, we're at this point here. The tangent line at that point is this. And so Vx at time equals pi over 4 is the slope of this tangent line. So let's look at this function and see if that makes sense. What's negative 20 times sine of 2 times pi over 4?
Negative 20.
Negative 20, yep. And does that make sense with the tangent line that I drew? Could that possibly be the slope of that tangent line? Yeah, right. We know it's negative. We know it's whatever. It is going to be. Okay, part C. Now we're going to do the same thing with the y component. So we want to show the y component of the velocity on a py versus time graph. So here's py, here's time. This is a sine function. So it's going to be like that. Pi over 4 is here. And a tangent at that point is this. So let's plug pi over 4 in for time in the velocity function we derived and make sure that those agree with each other. What's cosine of pi over 2? 0. And so the slope of this tangent line should be equal to 0. And is it? Yep. And then the last one. So now we're talking about the path of the motion, not talking about position versus time graphs. We're basically we're thinking about, like, if you were actually looking at the object moving, what's the path that it would follow? And what can anybody tell me what that path would look like? You could think of it like related to what you know about the x and y components of a unit circle. So anyways, this is just going to be a circular path going counterclockwise with a radius of 10. So px versus p, actually, let me. Okay, so this is px, this is py. The path is just going to be a circle, and it's going to be moving counterclockwise. And if you don't see that right away, you could, if you had an hour to figure out what this would look like, you could just plot points. Just choose a bunch of times. Time equals 1, time equals 2, time equals 3, and just trace your way around. But so that's the path. Where on this circle would it be when time is equal to pi over 4? Well, you could just plug in the values. So you'd be at an x position of 0, a y position of 10.
The bottom of the circle.
You're thinking of the velocity.
Oh.
So
Okay.
we're just talking, so it would be at the top. A tangent to the path at that point is this. Does that make sense with what we know about so this is at time equals pi over 4. Does that make sense with what we know from the position versus time and the px versus time and the py versus time? Well, we know that we should have a negative x component of velocity and a 0 y component of velocity. And this is a vector with a negative x component and a 0 y component. So that makes sense. If you can, the better you can make sense out of these sort of 4 different ways of looking at the relationship between velocity and position. So the 4 ways are the derivative relationship, the slope of the px versus time graph, slope of the py versus time graph, and the tangent to the path. The better you're going to understand what velocity is telling you overall. Any questions about any of those? Okay. Then the next thing we have to talk about is the acceleration vector. Oh, let me get this on here. The units, in 2 dimensions, the units are all the same as they were along a line. But the units for velocity are length over time, and the SI units are meters per second, just like in 1D. Okay, so now the acceleration vector. The acceleration vector as a function of time is just the time derivative of the velocity vector, which is the second derivative of the position vector. On a px versus time graph, concave up means x component of the acceleration is positive. And concave down means the x component is negative. And if it has no concavity, if it's linear, that means that the x component of acceleration is 0. And the same thing works for the y position versus time. So on the py versus time graph, concave up means the y component of the acceleration is positive. Concave down means ay is negative. And linear means ay is 0. Okay, so let's do a couple examples. So let's say that we have position versus time graphs that look like this. The x component of the position is that. And the y component of position versus time is that. What's the sine of ax? And b, what's the sine of ay? Okay, so for part A, what's the sine of, so if this is the position, the x position versus time graph on the left, what's the sine of the x acceleration? Positive, yep. That's concave up. So ax is positive. And then for b, what's the sine of the y acceleration?
0.
0. The y position versus time graph is linear. So ay equals 0. Here's another example. Let's say that the position as a function of time is equal to negative t 5t cubed. And we want to know what's the acceleration as a function of time. And then we want to know what's the acceleration at time equals 1 second. Okay, so how are we going to figure out the acceleration as a function of time? Yeah, take two derivatives. So we know that the velocity vector as a function of time is equal to negative 1 15t squared. And we know that The acceleration as a function of time is the derivative of the velocity with respect to time. So that's 0, 30t. And then, now we just evaluate it at 1 second. So when time is equal to 1 second, the acceleration vector is just 0, 30 times 1 equals 0, 30. We have that set of equations from 1D kinematics, the ones that at the beginning of class we derived, as part of the homework in the vector form. Is this a constant acceleration? Could we use those constant acceleration equations for this?
Yeah.
We could use it for the x component of the acceleration, but this is the acceleration function, and it's varying as time changes. And so, no, we couldn't use it for that because this is not constant acceleration. Most of what we're going to do is going to be constant acceleration. Okay, so now making sense out of velocity in 2D isn't too horribly hard, but making sense out of acceleration in 2D can be sort of tricky. So I want to talk a little bit about how to think about acceleration. So notice that along a line, when we were doing stuff in 1D, a non-zero acceleration means the object is speeding up or slowing down. That's because acceleration measures how quickly velocity is changing, and in 1D, that's all that can be happening if velocity is changing. So that's the only way velocity can change along a line. But that's not true in 2D. A velocity can change because the speed's changing. So in 2D, velocity can change because the speed is changing. Or because the direction is changing. In motion along a line, there's no such thing as direction change. And so in 2D and in 3D, we're not going to do calculations in 3D, but we live in 3D. The only way you have zero acceleration is when you have motion with a constant speed moving in a straight line. Okay, so anytime something's changing speed, it has acceleration. Anytime it's turning, it has acceleration. Okay? The only way you can have no acceleration is if the object is staying constant speed in the same direction. And if you look at a graph of an object's path, you can tell something about the direction of the acceleration. Okay, so I'm going to break this up into two pieces. The first one is the objects, whether it's speeding up or slowing down, affects the part of the acceleration that's parallel to the velocity vector. I'm going to call that A parallel. If it's speeding up, A parallel is in the same direction as the velocity. And if it's slowing down, A parallel is the opposite direction of the velocity vector. Okay, so notice that that's the same as our interpretation of acceleration with motion along a line. Along a line, if the acceleration and the velocity are in the same direction, we know that it's speeding up. If they're in opposite directions, we know it's slowing down. Now, that same thing is true if you only consider the component of the acceleration that's parallel to the velocity. Okay? And second, the turning tells us the direction of the part of the acceleration that's perpendicular to the velocity vector. I'm going to call that A perpendicular. And to think about that, you just have to sort of think, is the object turning left or right? Okay, so we're going to spend a whole lab doing this stuff, and it's going to come up in future labs too, so you get a lot of practice thinking like this. But let me go through two examples. I think I'm going to do one example, and then I'll have you try to work through one example on the board. Okay, so let's say that an object's path is like this. You can think of it as a px versus py, py versus px graph, or you can just think of it as like you're watching the object. Let's say this is the object, and it's moving this way along the path. And let's say at this instant it's speeding up. And we want to figure out velocity direction. We want to draw all these things on here. The part of the acceleration parallel to the velocity, the part of the acceleration perpendicular to the velocity, and then put those together to get a total acceleration. The total acceleration is just going to be, you can think of this as kind of defining a new coordinate system. The total acceleration is just going to be the parallel plus the perpendicular. There's nothing else. Okay, so the velocity is tangent to the path in the direction of motion. So that's the velocity vector. Any confusion about that? The velocity is always tangent to the path. This object's speeding up. So is the parallel part of the acceleration in the same or opposite direction? Same. So there's the parallel part of the acceleration. If you think about that ball being steered along the path by a mouse inside or whatever, you know, it's going this way. The mouse is like, is the mouse turning left or right? Well, that's what you have to think about in order to come up with the perpendicular part. Think about if it just continued straight, if it wasn't turning at all, it would follow these lines, right? So it's turning that way. You see that? And so the perpendicular part has to be in that direction. So there's a perpendicular. And now coming up with the total acceleration is just a matter of vector addition. The total acceleration is a parallel plus a perpendicular. So use the rules of vector addition. Put them head to tail. And the total acceleration goes from the free tail to the free head. So it's something like that. Now I drew the total acceleration as a vector as if we knew exactly what the direction was. But we don't know how big a parallel and a perpendicular are. So what do we really know about A? About the direction of A? It's that thing that early on in the class I said something about, oh, this was one of the problems that you asked me about. If we don't know we know the direction of this, We know that perfectly, and we know the direction of A parallel perfectly. But we don't know the magnitudes of them. A perpendicular could be this long for all we know, or A parallel could be this long. So we don't really know that A is in that direction. We just know it's somewhere in this quadrant. Okay. Does that make sense? Okay. So here's another example. I'd like you to work on this one. So the object's moving this way. Let's say this is the point A. This is the point B. And at each of these 2 points, draw the velocity vector direction, the A parallel direction, the A perpendicular direction, and the total acceleration. And let's say that it's slowing down the whole time. Okay, one kind of problem you're going to do a bunch of times is constant acceleration problems. So constant acceleration problems in 2D. For motion along a line, constant acceleration problems, you had 3 useful equations. Now we have 6. Just the x and y components of those 3 equations we had before. So Pfx is equal to P0x plus V0x Tf plus 1/2. That's getting to be too much for me. 1/2 Ax Tf squared. Pfy is equal to P0y plus V0y Tf plus 1/2 Ay Tf squared. So for motion along a line, that was a single equation. Now it's 2 equations, 2 components. And then the next 2 are Vfx is equal to V0x plus Ax Tf. Vfy is equal to V0y plus Ay Tf. And then the last 2 are 2 times Ax times the quantity Pfx minus P0x is equal to Vfx squared minus V0x squared. And then the y version of that equation, 2ay times the quantity Pfy minus P0y is equal to Vfy squared minus V0y squared. And to use these equations, we're going to go through the same steps as with 1D motion. The only changes are, so except instead of choosing a zero position and positive direction, now we choose an origin location and coordinate system axis orientation. And second, now when we list out all the variables, there's a whole bunch of them. There used to be, what? Acceleration, time final, PF and P0, VF and V0. So there used to be 6. Now there's going to be 11 that we have to work our way through. Time final, both components of acceleration, both components of P0, both components of P final, both components of V0, and both components of V final. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And there are 2 things to notice about these problems. These are 2 sort of useful facts. The first one is for these problems, we're often going to have to use an object's speed and angle to find a velocity vector. So like, for example, an object is launched at 25 meters per second at an angle 20 degrees above horizontal. And the way you'd use that information is your v sub 0 vector would be the speed, 25 meters per second, times the cosine and sine of 20 degrees. Can someone multiply that out for me? What's 25 times cosine of 20 and what's 25 times sine of 20?
Top one is 23.5.
Okay.
Sine is 8.5.
8.56. Okay. So we started out with this information about the speed and the angle, and we used that to get the vector components that then we're going to use in the equation. Okay, here's the second thing that you need to remember. And so when we were doing motion along a line, what did we know about the object at the point where it turned around, like when it reached the highest point, and like the velocity was 0? So the main thing we used that for was when an object reaches the highest point. So what do you think in 2D, what do you think is going to be the requirement for when an object reaches its highest point? Yeah, perfect. Yep, exactly. And so so when an object reaches its highest point, Vy is equal to 0, but not Vx. That's an easy mistake to make, to treat the whole velocity like it's going to be 0. But here's, I think this will help convince you. So take one of those, like, imagine taking one of those pitching machines. This is like one of them thought experiments. Okay, you know a pitching machine? Say get one that throws 100 miles an hour or something. Okay, and throw it up into the air, you know, figure out where the ball's going to go. And then once you have it all worked out, go to where the ball's going to reach its highest point. What? Kitchen machine. You could use it in a kitchen. Okay, and then once you figure out where the highest point's going to be, you run it a few times, figure out where the highest point's going to be. Get a step ladder and set it up there. And I have to draw you pretty short, no offense. Okay, and stand on top of the step ladder with your head right where the ball's going to go. Okay. And if you think about what would happen, I think it makes it more plausible that the entire velocity is not equal to 0 at that instant, right? Like if the whole velocity was equal to 0 at the highest point, that baseball would be launched at 100 miles an hour and get to this point and just gently knuckle up against the back of your head and sit there, right? But you know that's not going to happen. The y component of the velocity is going to be 0, but the x component of the velocity is still going to be 90 some miles an hour. And that would make this a really bad thing to do, you know? Try it. Draw straws for who has to stand up there. Well, let's do a couple problems. So here's the first example I want to do. And I think actually what we're going to do today, we're just going to do this one calculation. I'm going to show you one YouTube video, a Mythbusters video, and then that'll be it for today. Okay, so let's say a bullet is shot horizontally. A speed of capital V sub 0. At the same time, another bullet is dropped from the same height. Which bullet hits the ground first? Intuitively, I think to most people it seems obvious that the bullet that's shot is going to hit the ground a lot later than the bullet that's dropped. But it turns out that you can see it when you look at these equations. All of these equations are totally uncoupled from each other. The y equations only depend on y values, and the x equations only depend on x values. And so it turns out that the bullet doesn't care at all whether it has horizontal motion or vertical, horizontal motion or not. The vertical motion is exactly the same. So if you shoot a bullet, it'll hit the ground at exactly the same time as if you drop it. It's just going to hit the ground a long way away. Okay, so let's see how that works with the calculations. First, I'll do the shot bullet. So here's the gun. It's going to be a revolver because that's all I know how to draw. It has to be shot horizontally. Okay, so there's its initial velocity vector with a magnitude of v0. And if you think of that vector, putting that vector at the tail of a coordinate, the tail of that vector at the origin of a coordinate system, and the velocity, the initial velocity vector is equal to, v0 times cosine of 0, v0 times sine of 0, or you can also just think of this vector as being completely in the positive x direction. So either way, you get a vector of v0, 0. Okay, so now let's think of let's make our choices. So we'll choose a coordinate system with an origin on the ground beneath where it's shot from, just say beneath the shot. The x-axis horizontal, the y-axis vertical. And then time equals 0 is the instant that it's shot. Time final is when it hits the ground. And so now let's think about what we know. Do we know the time final? No, that's what we're trying to find. Do we know the acceleration? In free fall, it's always 9.81 down. So if our coordinate system is like this, that's 9.81 in the negative y direction. So the acceleration vector is 0, negative 9.81. Do we know the initial position? Oh, I didn't say the height, but I guess I better. So let's say the height is h. So when time is equal to 0, the position is equal to 0, positive h. Do we know anything about P final?
0, 0.
It's not 0, 0. The y position is 0, but the x position is going to be far away because we're shooting it out of a bullet. But yeah, we know that PFY is equal to 0. We don't know the x. Do we know anything about the initial velocity? Yeah, we figured that out completely. That's equal to capital V sub 0, 0. And we don't know anything about the final velocity. So the equation that works with these is PFY is equal to P0Y plus V0Y TF plus 1/2 AY TF squared. So PFY is 0. P0Y is h. V0y, what's the y component of the initial velocity? 0. Minus 1/2 times 9.81, so minus 4.905 TF squared. And so TF is equal to plus or minus square root of h over 4.905 square root. And the thing to notice is that capital V0 never came into the equation. So you'd get the same time, you'd get the same TF if the initial velocity vector was 0, 0. Okay, and that's sort of hard to wrap your head around for most people, but let's watch a video that shows that it works that way. Let's see.
Same second, except one bullet is dropped to the ground, the other is fired from a gun. The classic physics thought experiment states that both bullets will hit the ground at the same time.
Based on what theory?
Based on the theory that the bullet that's fired from the gun has no wings on it, no lift. Thus, gravity has the same effect on it as it does on the drop bullet, and thus, they hit the ground simultaneously.
Adam lays down a runway of white paper so the high-speed camera will clearly see and measure both bullets at the same time, in the same place, and in the same shot. All we need now in the drop zone is Jamie's drop rig, so the boys can take a shot at physics history.
All right, dude, you ready to do this for real?
I think we'll hit it on the first shot.
Really?
Oh, yeah.
You never make predictions. That's awesome.
Bullet drop versus fired. In 3, 2, 1.
But from 360 feet away, the boys can't see exactly where the fired bullet landed.
Let's go see where it hit.
So Adam takes a one-wheeled ride down the room to check out the drop zone.
Wow.
And the results are simply ripping.
Can't get much closer than that. Oh, I can't wait to see the high speed.
Adam analyzes the high speed and crunches the numbers.
3677 minus 3915 equals 238 divided by 6. Dude, the difference is 39.6 milliseconds.
Which means it's less than the human eye can make out.
So after days of brain-teasing tests, the Mythbusters can claim a world first for themselves. And a victory for physics.
Let me put 39.6 milliseconds into some perspective for you. When you go to the movies and watch a projected celluloid film on the screen, you know that that film's made up of individual images, right? What you might not have known is that it takes 24 of those per second to make up the film that you're watching. So each one is on screen for exactly 1/24th of a second, but you don't notice that because it's faster than your eye can register. Well, that 1/24th of a second is actually longer than 39.6 milliseconds. That's how close those two bullets were.
And I think probably the explanation for why they were off that far is just like trying to get the gun to be horizontal, trying to get the things to be dropped at the same time. So yeah, it really does work that way. Surprising. Okay. All right, that's all.